So to start as simple as possible, we will start with two-dimensional space, okay? So in two-dimensional space, you are used to describe the position vector using two numbers, x and y. And what do those two numbers mean? So basically, if we have an axis x and y, we have the two axes, and you are trying to describe some point in this space. So what we give is the x number, which is the x coordinate, and the y number, which is the y coordinate. Those are rectangular coordinates, also called Cartesian coordinates. Now, the first coordinate system that we will learn is polar coordinates, okay? So polar coordinates is when we describe the positions in two-dimensional space, not with x and y, but instead with these two numbers, rho and phi, okay? Rho is a distance, the distance from the origin, okay? So the distance of this line here. And phi is the angle in the xy plane, and we normally define it as a convention. Everybody usually defines it as the anti-clockwise angle from the x-axis, okay? You are actually familiar with a very similar system when you work with complex numbers. You can either work with real and imaginary parts, which would correspond to x and y, or you can work with the complex amplitude and the complex argument of a number, which would correspond to rho and phi, okay? The way we define rho and phi in terms of x and y is written here, okay? So x equals rho cosine phi, y equals rho sine phi, and that's very simple to do by noticing that this is a right angle triangle and doing some trigonometry. You can also find rho and phi in terms of x and y, okay? So this is like two ways of writing the same correspondence. So rho is just the distance which corresponds to the hypotenuse of this triangle, so it's the square root of x squared plus y squared, while phi can be obtained, if you know y and x, by doing the inverse tangent, because you know that the tangent of phi will be equal to y divided by x. Therefore, phi is the inverse tangent of y divided by x. Now, very quickly, let me show you an applet of how polar coordinates work. So to show you these applets, by the way, I'm using a software called Mathematica. You can see the name here, and you can actually obtain Mathematica for yourself by, you can ask me and I will give you a link. So every student in King's College can have a license of Mathematica in your own computer, okay? So it's a very nice program. So it's like a computing language, but also it's very useful for plotting things. So I use it to plot applets like this one, where I have now here two sliders, r and phi, and I can change the value of r and the value of phi, and you can see how the point moves as I change them, okay? Okay, so this sounds very simple, but the questions that I can ask you about this can turn out to be not so simple. So that's why I'm going to next show you some examples of some curves written in polar coordinates. So let me first do a very simple example. If you wanted to describe a circle, you know that in rectangular coordinates a circle is quite ugly because it's x squared plus y squared equals r squared, right? So it becomes an ugly equation with squares and so on. But how do you describe a circle if you are in polar coordinates? Actually, it's very simple. In polar coordinates, you can just say rho equals r, and that's it. That is the equation for a circle, okay? If you want to be explicit, you can say that rho equals r and phi is moving in the interval 0 to 2 pi, which is a way of saying like you are moving all around the circle. In that way, you could, for example, describe a semicircle by limiting those angles to, for example, 0 to pi, and that would be only the upper semicircle, okay? So you can see that writing things like circles can become very simple in polar coordinates. But in the next videos, I'm going to show you some not so simple functions in polar coordinates.